Okay, in this video, we're going to continue our development of our negative edge triggered D flip-flop into a 4-bit shift register. So first thing to do is probably to show you what that looks like in Magic. So I've actually done the actual work of creating the 4-bit shift register in Magic. And I did that by creating a new cell called sreg. And let me see. Documents, and I put this in neg D flip-flop. And originally it was just an empty cell. I'm going to set up the grid here. Grid 0.05 um, 0.05 um, snap user, drc style, drc full. And what I did was I basically connected the 4 shift registers together, 4 D flip-flops together, and overlap them partially here by 3 grid units, so that the metal from the VDD and ground rails just touch each other. So I can show you what that looks like here. And you can kind of do this incrementally. You can figure it out beforehand and then put the box where you want the lower left-hand corner to be, and then go colon get cell to actually get the cell instance in place. You can also move the cell instance around by selecting the cell and then doing colon move, west 1. If you need to fine tune it, sometimes you'll put it down. You'll see some design rule violations because the metals aren't quite touching each other, but they're below the design rule for metal to metal spacing. And so by moving it one grid unit at a time, you can make the little white dots go away, and sometimes that's how it works out. But the other thing which I've done here is I've designed an inverter cell to generate D bar from D. So if you remember how if you remember how this negative D flip-flop cell works, the 2 D bar inputs come in on poly here on the left-hand edge of the cell, at the bottom and the top, and the actual connection between them is made in the right-hand side of the cell that's to its left, right? So here the polysilicon, the poly contact is made, and that poly is used to route these 2 together all the way through the cell. But instead of having to do that both in the right-hand edge of the cell and the left-hand edge, for the sake of making these 2 inputs one input, I've elected to make them be 2 separate input ports, and I'm taking care of generating the D bar with this sort of end cell that I'm putting on the left-hand end of my shift register. So here I have this inverter. Here's the VDD connection, the PMOS transistor, the ground connection, the NMOS transistor. Here's the common drain connection in the inverter. The input comes in metal 1 from the left, makes a contact down to local interconnect and poly. The local interconnect continues on and connects with the D input of the first stage of the shift register. The output of the inverter goes down here, makes a poly contact to connect to the D bar input down here, and it goes up here and makes a poly contact to the D bar input up here of the first stage of the shift register. I've also kind of extended the well out here, even though the well for this cell doesn't have to be as tall as the well for the shift register. I've just made it the same height, and I've made the VDD rail and the ground rail the same height as they are in the shift register. And so that's one cell which I've laid out here. Let me select the whole thing and Shift X to hide them, just so you can see the other things that I've done. So I drew a little bit of metal 1 for each of the ports, or each. Actually, I haven't made ports at this top level cell. I've just put labels on for VDD, MD, ground, and this is the clock. And then I've taken the outputs of the shift registers. So if I show this one and zoom in here, this piece of local interconnect up here happens to be the Q output of the cell. So that is a convenient place to take to have sort of like a parallel output from my shift register stages. And so what I've done here at the top level, if I hide this, is I've drawn a little piece of local interconnect here to attach the label for Q0 here, Q1 here, Q2, and then Q3. And I think I've called, yeah, so I called the top level label for the VDD rail VDD, and I've called the top level rail for the ground rail ground. Okay, so that's the shift register. I did lay out that extra inverter cell. And let me zoom to the whole thing. And so now I'm going to extract a top level net list for this whole thing. And we'll see what that net list looks like. So I'm going to do extract all, extract and then I'm going to do ext to spice hierarchy on, ext to spice scale off, ext to spice C-thresh infinite to set the to set things up so that there are no capacitors and no parasitic capacitances written out into the netlist. Then I'm going to run ext to spice, and we can pull up another terminal window and see what we got. So sreg.spice will be the name of the netlist. And so because we have not put ports in our top level cell, we don't have a sub-circuit wrapper around the top level cell. We just have the instances of the subcells. So we have an instance of the inverter and 4 instances of the negative D flip-flop cell. And I guess I should also say that I went back into the negative D flip-flop cell and I changed the labels back into ports so that I could extract a hierarchical netlist here and have the pins in the subcircuit correspond to the ports that I made, and I defined the order of the ports to be basically the same as I had discussed last time. And so you can see also the here's the inverter subcircuit, here's the negative D flip-flop circuit, and here's the top level. So that looks good. There's no random capacitors hanging out. So the next thing to do, if we want to do LVS on the whole shift register, is to create a schematic in Xscheme that would correspond to our magic cell. Okay, this will not have any test harness stuff in it, no VDD voltage source, no input voltage sources, no clock voltage source. no transient simulation, and no library model or model library. And so the first thing to do would be to use Xscheme to create a symbol corresponding to our negative D flip-flop schematic. And also, let's see, if I do Xscheme, neg D flip-flop dot sch. I did alter this schematic slightly from the last time you saw it. Last time I was I had this VP pin label and this VN pin label were actually connected to the VDD and ground flags, and that was to make the body connections of the 3-terminal NFETs match up with the connections to the sources here. And so that was what you need to do if you're going to use the 3-terminal MOSFETs for your schematics to do LVS. And it was a good thing that we did LVS at this level, because we found an issue, if you recall, and we were able to make the netlist match at this level. And so to move up one level in the hierarchy, we basically changed out the ground net for the VN pin and the VDD power flag for the VP pin. Okay, and then saved it. And then we created, or then I created a symbol. So we're going to open up the symbol just to show you that. So it's negdff.sim. And so that is just a box, and I've got a D input on the left and 2 D bar inputs on the left, and I've got a Q output on the right and a Q bar output on the right. This is my clock input down below, which kind of corresponds in the layout to where the clock is routed along the bottom. This is my power VP power pin. This is my ground or VN power pin. And if you don't have anything selected and you hit the Q key, you can see the property for the whole, like the property dialog for the whole symbol. So this is a type subcircuit, which means there's also a schematic file that has the same name. And then the format, this line is the template for what gets written out at the beginning of the subcircuit definition. So there's the instance name, which will be X followed by some number here, then the pin list, and then the symbol name, which is the negdff, which would correspond to the subcircuit name. And then the template basically says I want the name of this cell to have the format X. That's the prefix that's for a subcircuit in SPICE, and then a number. And 1 is the first number. If there is already an X1 in the circuit, it will automatically give you a unique number there. So that's why it's a template and not the actual name. Okay, so I'm going to close this down. And so that's my symbol. It's maybe a little bit larger compared to like the voltage source symbols and the transistor symbols than I might like in retrospect, but yeah, it's serviceable. So then my shift register schematic for LVS purposes looks like this. I basically instance 4 copies of my negative D flip-flop symbol. X1, X2, X3, and X4 were the names that they were given. And then I hooked up the VDD flag and the ground flag to the power pins. I basically just copied over my inverter symbol from the buffer tutorial, or the inverter tutorial that we did earlier. That schematic and that symbol correspond nicely to the specialized inverter symbol that or the inverter layout cell that I made to go to the left end of the shift register, but I can reuse my old inverter schematic and inverter symbol from the previous tutorial for that. So my D input comes in here to the D input of the shift register. It goes through the inverter, and that feeds both of the D bar inputs to the first stage. And then I make a connection here and a little parallel side tap off for the parallel output. So here's the serial input to the next stage and the parallel output. I'm forking QN and connecting that to the two DN inputs of the next stage here, and so on. The clock, I'm just routing across the bottom here and connecting to each of the pins. You could do that through net labels if you wanted to. And so anyway, you can then click on net list. It's highlighting these nets because they are not connected to anything other than, inputs here. There's nothing driving these input pins, and this output pin is not connected to anything. And it's highlighting this down here for the same reason. It's an input pin. It's not driven by anything, but that's okay. This is just for generating a netlist for LVS purposes. So we're going to close this down, and the netlist is going to live in twiddle/.xscheme simulations and sreg.spice, and then we'll call it sreg xscheme spice in this directory, and we'll take a look at it. And so you see we have 5 at the top level. We have 5 subcircuit instances, 4 negative D flip-flops, and 1 inverter. And then we have the subcircuit definition for the negative D flip-flop, which has 24 transistors in it, which is the right number. And then here's our subcircuit definition for the inverter cell. So that looks good. And we can then run LVS on sreg xscheme sreg spice, which is the magic one, and we have here 98 devices and 53 nets in both circuits. The circuits match uniquely, which is good. So it's always a good idea to ensure that you do LVS comparisons at each level of the hierarchy. So if we hadn't reconciled the negative D flip-flop layout, which is a fairly complicated cell, with the schematic in the last video, you could imagine we get to this point where we have 4 of them in a higher level schematic, and we started doing LVS matching here. It would have been much harder to figure out what the issue was. It was hard enough to figure out what it was in the last video with just one cell. If you imagine having 98 transistors and whatnot instead of 24, it could be quite a lot harder to figure out what things were going wrong if they hadn't matched. So I always recommend that you do LVS kind of incrementally as you go as a good practice. Okay, so that's constructing the shift register in Magic and doing LVS on the shift register. And so now I want to go through some stuff about doing the transient simulations. So what we're going to do is we're going to simulate the 4-bit shift register. We're going to hopefully simulate shifting an input into the left-hand side and having it kind of progress from one stage of the shift register to the next, to the next, to the next. And so to do that, what I've done is I basically opened up my shift register schematic, and then I've saved it as a different schematic file so that I can add the test harness stuff to it. And so I have done that in xscheme. It's sreg_tran .sch. Okay, so here's my test harness. So here's the same schematic that I had before, and I haven't changed anything about it. I've just added stuff to it. So I added a VDD voltage source between the VDD power flag and the ground power flag, and I set it to 1.8 volts. I have created a clock voltage source, and I'm using the same parameters and the same clock setup as I used as my signal for the inverter tutorial. So I'm using a 10 nanosecond period. I'm using 1 nanosecond rise and fall times, a 4 nanosecond high time, so you get a symmetric high and low time, and then low level is 0, high level is 1.8. So this is a 100 megahertz clock. And for my D input, I'm using a piecewise linear voltage source. And the way a piecewise linear voltage source works is that you specify time voltage ordered pairs. So here I'm starting at 0 seconds and 0 volts, 25 nanoseconds, I'm at 0 volts, 26 nanoseconds, so that's 1 nanosecond later, I'm up at the high level of 1.8 volts, and then 40 nanoseconds, I'm at 1.8 volts, and then at 41 nanoseconds I go back down to 0, and it just maintains that last level of 0 volts for the remainder of the simulation. It joins these points, which are sort of the control points, with straight line segments. So here it's going from 0 to 0, so it's a low level for 25 nanoseconds, and then it's a straight line ramp from 0 volts up to 1.8 volts in 1 nanosecond. Then it maintains a high level for, what is that, 26 to 40, that's 14 nanoseconds, and then it goes down again to 0 in 1 nanosecond. And that's going to be a fairly convenient way to define your waveforms if they're not just simple periodic clocks like that, like this one is up here. I very often will use piecewise linear waveforms for that sort of thing. And then we've got our typical model library. We've got my transient simulation, my time step. My maximum time step is going to be is this 10 picoseconds, a hundredth of a nanosecond, and then I'm going to simulate for 100 nanoseconds, which corresponds to 10 cycles. And let's just see what that does. So I'm going to write the netlist out. I'm going to simulate. It's going to take a little while to simulate. Not terribly long, but a little while. Okay, it's done. We'll dismiss that and we will launch GAW. Okay, to look at this, what I'm going to do is I'm going to add some panes. So I'm going to add panels. So I'm going to add 4 panels so that we can put the clock, the input, and the 4 output waveforms in these different panels. So let's put the clock down here. Here's the clock. There's my clock, 10 clock cycles. We put the input up here. So there's my pulse that goes up after 25 nanoseconds or whatever, and goes back down at 40. Put Q0 here. Put Q1 here. sorry, that's QN1. All right, we'll put Q1 here. Put Q2 here. And we'll put Q3 here. Let's see. Okay, so right. So this is kind of what we might expect to see, right? So the pulse, when the pulse goes high, it doesn't propagate to the first Q output until the falling edge, the next falling edge of the clock, which it does, and then we don't shift that over until the next falling edge of the clock. So this pulse propagates to the next stage on the next falling edge of the clock, propagates to the next stage on the next falling edge of the clock, and then finally it arrives at Q3 on the next falling edge of the clock. So this is all good. So what's up with this? Well, the answer is that we have a bistable kind of circuit, right? So there's two possible ways for the cell to initialize itself. You could have the 0-1 state or the 1-0 state. And just because of the numerics of the way that the transient simulation is worked out, it has chosen to make the output of the first stage initially high. Okay, and so that high pulse propagates along earlier in time than our input pulse gets there. And so we still get the same kind of shift register behavior, but it's doing kind of its own thing on the initialization. So how can we fix that? Well, we can fix that with the help of something called initial condition statements. And so we can add those to our little code block here. And so if we wanted to, for instance, set the initial condition for the Q outputs so that they're all low, we could go .IC and then V, the voltage on Q0 equals 0, the voltage on Q1 equals 0, the voltage on Q2 equals 0, and the voltage on Q3, we want that to start at 0 as well. Okay, so we're going to try that. And we can save this. Can write the net list out, and then we'll simulate it, and we'll see what happens. Okay, we'll launch GA and see what we got. Okay, we can add our 1, 2, 3, 4, and put the clock down there, put D up there, and we'll put Q0 there. Q1 there, and already we see we have still some issue. Q2 and Q3. Okay, so the situation is slightly different. We're not getting quite as wide a pulse that's propagating here, and some other initial garbage that we saw on some of the later stages. But what's going on here? Why is this output refusing to stay low. In fact, it looks like it started low, but then it goes high here. The answer to that is that if you think about it, there's actually two bistable circuits in each of the D flip-flop cells, right? So there's the two transparent latches that each have a bistable circuit in them. So by setting the initial condition on the Q output, we only initialized the state of the second of the two bistable circuits in each subcell. So if we want to get the whole thing to initialize cleanly into the zero state, we're going to actually have to go in and set initial conditions on the outputs of the intermediate node of between the phi latch and the phi bar latch. Okay, so to do that, we're going to have to identify the sort of hierarchical net name that we would like to set with an additional initial condition statements. Okay, so we're going to close down GA. And let's look at our net list. So if we edit the net list, we can look at the let's see, what's the best way to do this? So let us go, I don't want to look at the net list. What I want to do is I want to go down in the hierarchy. So if I select this cell and I hit Shift, or I hit E, okay, that brings me down to the schematic underneath the symbol. And what I'd like to do is I'd like to take this node right here. This is the Q output of the first latch stage. Okay, and what I'd like to know is what is the name that's been given to this. Since I didn't give it a name, Xscheme decided on the net name that this would be given, and so it's going to be the gate of M15. Okay, so if I go back up, which I think is Control E, and I look at the net list, it was the gate of M15. So XM15, the order of the pins here is drain, gate, source, bulk. And so net 7 is the name within the subcircuit definition of the net that I would like to initialize. Okay, so net 7. And the way that you access net 7 of subcircuit X1 would be as follows. So we're going to do another IC statement here. We could do it all on one line, but just to keep the line from becoming really long, we're going to go V of X1 dot net 7 equals 0. So it's kind of like a path name, but the separator is not a slash, it's a dot. V of X2 dot net 7 equals 0. V of X3 dot net 7 equals 0, and V of X4 dot net 7 equals 0. Okay, let's save that and let's try seeing what that looks like. Okay, we'll go to GAW. And we will create some extra panels here. And again, we will put clock in this one. We will put D in that one. We will put Q0 here. Q1 will go there. Q2 will go there. And Q3 we'll put there. And so this is just what we would like to see. So the initial state of all of the shift register bits is 0, and we don't have any extra little bits coming out here, any little pulses coming out from the internal states not being properly initialized. And we have our sequence of 4 successive pulses here that are aligned with the falling edges of the successive clock periods here. Okay, so that's about it. We could also take our negative D flip-flop, and by sort of rearranging the geometry so that the other latches before the latch, like we exchange the phi and the phi bar latches in their order, we would create a leading edge triggered flip-flop. And of course, we could go through that exercise, but it would be very similar to this whole thing, so we're not going to bother doing that. So, hope that helps, and you should be doing something fairly similar to this with Mini Project 2, only on the CSRL latch and CSRL flip-flop, and hopefully this will help you kind of get going on that project. So we'll see you next time.